afternoon, everyone. Today's Richardson project to solve our sensing plan. First of all, I'm introducing the teammates. First, we have John Garcia and Gabriel Sosaya. They teamed up to mostly work on the software side of the project. Next, we have Sakir Mohammed and myself, Omar Vasquez, and we teamed up to mostly work on the hardware side of the project. Now, the way this project came about was because of the hot climate. We wanted to design a fan that would track a person's motion. And we also, some of the goals that we had in mind was to design a device to be convenient for people in developing countries with limited access to electricity. We also wanted the device to have the following characteristics: to have a motion tracking system, to be solar powered, to be power efficient, and inexpensive. Now, from the last semester, we made a few improvements and adjustments to our prototype, but we still continue to use the same simple approach. As you can see here, we have a solar panel, a power management card, and a rechargeable battery. As compared to last semester, we were powering the system through a USB cable from a laptop. Last semester, we were using 2 passive infrared sensors to cover 3 different zones. This semester, we went ahead and added a 3rd sensor. We continued using the same microcontroller, the Arduino Uno, and of course, we have our fan and the servo to rotate the fan in the appropriate direction. Now, based on feedback from last semester, we went ahead and added a small sequence adapter swamp cooler. And what it does is, if you just pour ice cold water into the container, as the water evaporates, the fan is blowing the evaporated water into the air, causing it to be cool. Now, the way this project works is, as you see here, we have 3 different zones. And if a person were to step into one of the zones, the fan will turn on and face in the direction that the person is standing in. Now, we have multiple personnel, then the fan will turn on and rotate between different personnel. And if there's no detection, then the fan will turn off. And some of the results we have, as you see here in the small pie chart, the total current consumption for each component. The total current consumption for the whole system is 490 milliamps, and about a power consumption of 2.45 watts. Now, we also went ahead and ran some trials with the swamp cooler, and we managed to drop the temperature down by 10% indoors within the small proximity of the fan, and outdoors just by 2%. Some of the challenges that we faced for the project was the design and housing for each sensor. We wanted to concentrate its capability within each different zone. And also we had to recode the software to add the 3rd passive infrared sensor and be able to detect multiple personnel. And also last semester, the servo had a starter-like movement or fan. This semester, we were able to get the servo to do a smoother transition between each different zone. We have the actual working prototype on our table. If you'd like to come by and visit us, and answer any questions that you may have at this time. Yes, sir.
490 milliamps was your current budget. How much of that is the fan? How much of the 490 milliamps is the fan?
Well, that's actually the whole current consumption for the whole system, not just the fan.
Right.
And it's 90 milliamps is just going to the fan.
So the servo is the #1 power consumer in your system, or what's consuming all the power?
Actually, the Arduino is the one that's consuming most of the power because the current is flowing into it, and it also has to send and receive the different signals to each component.
Which goes back to one of the comments earlier. From here, all the information is there. From here, I can read it and get. From there, I cannot. So I'm guessing that you cannot see from here.
So the blue is
pie chart.
Yes,
Next time, please use bigger fonts or because it's not a readable.
Well, I would like to point out that your requirements are that you have 1 poster. Now, in reality, you would have multiple posters, but for this academic environment, you have 1 poster. And so therefore, to put all the data on there, you have to compact it. So it's not totally fair to totally blast you on a small farm.
yes, sir.
So just another question on the evaporator cooler. What delta do you see in temperature? With that? I guess I've seen a lot of the sponge, but the one that just has a bunch of water sitting on the bottom, I actually haven't seen that. You know what type of gradient you see in temperature with the water version versus, just out of curiosity?
We actually haven't tested it with a sponge, but we just took a simple thermometer and then poured the water on there, and then to turn on the fan and just use it and then measure the temperature. And also we'll test it before putting the ice cool water in there and then using the ice cool water.
And what did you see with the water? That it's like 10 degrees cooler on one side with the fan going? Was that what, something?
Yes, roughly about 10 degrees, but of course, just being close by the fan.
I'm just more curious about that question. So 10 degree change in how much time? Because you're almost sort of replacing the market for cooler and third world beverage. So I'm curious what 10 degrees and how much time?
We tested it with 5 minutes and 10 minutes, but within the 10 minutes, we were able to drop it down to 10%.
That's the feeder.
And if I could just ask one more question about inexpensive wood, you guys are charging the battery or something, often.
Well,
It's 6 volt, right? It's like 12.
this battery is actually a 4-volt battery.
Okay, so that's like a $5, 5 amp hour.
It's 9
It's 9 amp hours.
The overall cost of the fan is.
Well, as we have the design right now, it's 125, but if you were to put it into market, it would be about $57.
$57.
And that's just like one-time buy, you just buy it and
Right, so I guess we can thank the speakers.